Okay, this hour we are going to speak about rudder, but I call this lecture as rudder hydrodynamics because we will concentrate more on this performance part of it, which is because of hydrodynamics. See, as you know, there are various kinds of rudder. I do not want to go into the detail. There are rudders which are like balanced, not balanced, having a post. Number of types of rudders are there. Okay, essentially rudder is a device which you can rotate about some axis, and by rotation it causes primarily force in the y direction. This is what you are interested. You want to generate turning moment and turning force. This is what exactly it is. So if you take a rudder here, something like that, it has got a rudder stock. It might have earlier as a rudder post, but as I said, I am not getting into the detail of the construction part of rudder. In fact, there used to be a empirical formula about the rudder area also, how much it should be. It turns out approximately 2% of the central plane area of the rudder, or some other formulas are there, like some empirical type formulas, d into L by 100, something like that. I will just give you one formula here, etc., etc. And this the various kinds of formulas. It obviously it is dl by 100 gives you the percentage. The dl is the, for a ship, the center plane area, more or less this area. So AT is some kind of percentage of that. As I say, if you work it out, this will turn out to be again around 1 or so, 2% or so. The purpose of today's now talk is that how rudder produces force, how the cross section look like, and some detail regarding its performance. Okay. So if you take a cross section of the rudder here, typical. See, this is a simple rudder. Actually, rudder will have many other shape. It can be triangular, it can be whatever. But if you take a cross section of the rudder here, invariably now this rudder will look like a aerofoil section, a symmetric aerofoil section. Okay. Let me draw from here. The rudder will be looking like a, I will just draw in this way, a turned rudder. It will have a symmetric aerofoil section. This is a typical cross section if you take, and I have assumed that it has been turned little bit. Okay. It will be turning about some point here. This may be the rudder stock point or spindle, I can call an axis about which it is turned. Okay. Now you have a force coming here, I mean the axis, let us say like this. So velocity comes this side, and I can call this to be angle of attack alpha. Let me again say, if you take a cross section of the rudder, see, first of all, why cross section for hydrodynamics? It is only obvious because you would expect the flow along the rudder to be along this line, not having a vertical motion much. So any cross section you take, you can find out, and you can take each cross section, add them up, you will get the total force more or less. So therefore cross section is very logical approximation, and I will just want to show or tell you what kind of forces etc. will be acting on that. You will have a rudder spindle here. Of course, this is a symmetric aerofoil section. Let us use the word hydrofoil. There is really not much. It is symmetric because mostly because you want it to have same performance both sides, not like a airplane where you have an unsymmetric aerofoil, because you wanted the ship to only plane to only go up, not down. Okay. Similarly, propeller, you only want force in one direction mostly, therefore it is not symmetric. But in this case it is always symmetric because either turn port or starboard you want equal kind of forces. Now if you have a velocity coming here v, what happens is, as you all know, it is going to produce a force in some direction. Primarily there will be a component in this direction which is known as lift force, and there is a component in this direction which is called as drag force. Okay. There will be, therefore, if I combine the two here, this is my net force, sorry, this will be my net force that will come. Okay. See, by definition in aerofoil there is a force there. You can call it this way, that the net force is this force, say F. This F is broken in two parts. One is what is called the force component normal to the direction of the velocity, that is known as lift force, and along the direction of velocity, that is called the drag force. These two will depend on alpha. These two together is this F, and you can also find out, resolve them in terms of the two component which is along the normal and along the tangential part of it. That is, I can call this with normal force, I can call this with tangential force. All are actually same part. The reason we are writing that is because you will find out that if suppose there is a ship here, see ship is along this line, which may not be the case always, then I want to find out what is my force coming, okay, along the direction which may be normal to this axis, and we might have to break it in various parts. So, we might want to know actually various kind of force components. Okay. Now, let me see, this is actually, let me call it P. P, before that let me say like this. In all aerofoil theory, in all hydrofoil and aerofoil theory, first of all, this lift and drag force are well known, and I am probably not going to go to this hydrodynamics so much, but I just want to tell you why this force comes. Is there is a very simple reason. Very simple reason. If you have a plate like that here, when the flow comes, it basically goes like this and it goes like this, okay, and it comes down like this when the flow comes. Now, it turns out that this distance is longer than this distance. So, one can show that if there is a point of fluid, then it has got a velocity here which is up and velocity here which is down, because it must travel the same distance and meet up here at the same time. That is what one can show actually, but the top one is to travel longer distance than the bottom one. So, it turns out that the velocity of the particles on the top is little more than the bottom one. As a result, now there is Bernoulli's equation says that half into v square plus p plus some gh equal to constant. There is a famous theorem which says that velocity square plus pressure plus some hydrostatic head is constant. Now, it has the same hydrostatic head, therefore, v going up means p coming down, this means p going up. So, there is a larger fluid pressure here, then there is more pressure there than this side pressure. So, the net thing will give me a pressure on this side. That is why there is a force that comes out ultimately this way. This is a mechanism, this is all aerofoil theory, whole lot of stuff is there, we need not go through that. No, symmetric, unsymmetric, in fact, even if you have a plate here, this is what is called aerofoil theory. You see, this is a different theory, we need not go through all that stuff, but I mean, it's difficult to tell, but I'll tell you another interesting part here is that something like that. See, just spend little time, because we are calling the lecture as Rudder Hydrodynamics. So, let me tell about this aerofoil theory a little bit. See, you have this aerofoil or something, I'll tell your answer. It turns out that if there was a flow coming here, if you draw a streamline, it would have actually come like that and it would have come out like this. If you assume some standard flow solution, it would have shown like that, it would have actually gone like that, flow would have come like that. But it turns out that if this has to happen, there is a stagnation point. See, there is a point called stagnation point where pressure is supposed to be 0, velocity is supposed to be 0. Okay. Now, if this was the case, then the flow has to come like that, there has to be some streamline like this, but that is not possible. Okay. Since this is not possible, you might have to, you know, it is, you can think that somebody has to as if put a circulation, as if I am trying to rotate this flow and push this point down to here. So, as if I have introduced some kind of rotation. So, you know, this becomes same as a ball, because I want this separation to be like here, I am introducing a circulation, as if I am trying to induce a motion like this here, It's all difficult concept, but it is something like there is a ball there, I am trying to rotate the ball like this in order to induce a motion like a circular motion. And you know cricket ball, if you do that, then you get a lift here. So same way here, if you do that, it turns out that you can get a force here which is this direction. This is the mechanism, but you know, it's all complicated aerodynamic theory. All you need to know right now, the same principle for which propeller works, aerofoil works, etc. And the same thing will apply to answer your question even for a flat plate. Even if there is a flat plate here, even then the flow comes like that, and it has a lift. It is simply that the lift here is not so much as you want. If you put a aerofoil, lift is much more. Since your objective is to get more force in this direction and less force in this direction, therefore you want to actually have a design, you want to design a section where you get more and more this L, which means you get more and more this you know, the difference of pressure in the two, but not so much more that this pressure is less than vapor pressure, then cavitation comes in. That's a different thing. But this is why even if when a ship is yawing and going, it also acts as a lifting. So when the ship also travels like that, you know, a full ship, it actually gets a force, lift force in this side, because whenever the flow goes like that, this produces a lift. It becomes what is known as a lifting surface. Okay. So anyhow, this is a different theory, we are not going to so much talk about that, but coming back to this diagram, it will turn out that if you have a section here, if there is a flow there, it will always produce a force somewhat in this direction, and you want this direction to be more and more this side, because you want more and more lift. In fact, that is what will happen. You want more and more, you want much more L than much more of L than T. But regardless of that, for all aerofoil theory, you get this, and it is usual to express these forces in terms of such coefficients, AT being the transverse area and a drag force as D by, you can also call this Cn as N force by it's a common trick that any force, see if you see the unit of force, okay, you see that the non-dimensional part of force becomes equal to half rho v square into area. This becomes the non-dimensionalization part, and you always call that to be some coefficient. And you see, it's a fluid dynamics trick is that whenever you cannot figure out a force, you simply call the force equal to some coefficient into half rho v square into an area. How you are calling Cf, half rho v square into surface area. How you are calling your C total resistance, half rho v square area. So this is nothing but a way of non-dimensionalizing the force, and you call that unknown thing as a coefficient, and that I don't know, I have to find out. So you find out. So similarly also here, in terms of instead of getting L and L and D and N and T, you always express them in terms of coefficient, and the best way is to just divide by half rho L into v square into AT. Why in this case this? Because it is obvious that it will depend on the ambient this velocity. More velocity means you expect more force. It will depend on the area, because more area means more point for pressure to act. You know, if you make it bigger, more point the pressure will act. So more difference will come in. So it's obviously it is written like that. Okay. Why I say that is because there are when you want to finally design, you will find out that for any rudder, ultimately for a known section, CL and CD, mostly CL and CD are available. Data banks are there for various sections, because it is such an extensive topic. Thousands and thousands of experiments have been done for many known sections, NACA and various Taylor profile, and CLCD are available. So we are not calculating CLCD, we are basically going to use those CLCD part, and it turns out for many sections the typical CLCD part will look like something like this, that is an angle of attack alpha, this is an angle of attack alpha. It turns out that CL and CD, one of them CL, normally it need not be always 0, but somewhere here, let us say somewhere here maybe, it goes up there and then actually at some point it stalls. This is up to normally around 30 to 35 degree for most of the common sections, and CD initially starts from high little bit, and then of course it still goes up, and there is a CL by CD. This may be CD, this may be CL. This is actually the coefficient in C's. This is angle. Typically it looks like that. Typically this is exactly why in fact you do not have the rudder angle and all more than 30-35 degree, because your idea is to get lift. There is no point of not getting lift and getting only drag. You have a rudder like that, you are getting no lift force but only drag force, there is no point. You are not bothered, you basically want the lift force more. Okay. In fact, you want as much lift as low drag, that is what your ambition is. Anyhow, going back to this diagram once more, this diagram we can easily find out that if I call L and D and if I know this angle alpha, I can actually resolve all this P and all. See, P becomes, for example, P square is L square plus D square, then you can say that P into cos of this angle is L, P into sine of this angle, you know, in terms of this angle, this angle, this angle, we can make all the sort of we can resolve all of them. This is alpha, so this is actually, this part is alpha. Okay. So I will just write down this expression, that is very simple, because I am not. The problem of this course is, of course, that the space is the problem. So P becomes L square plus D square, N becomes it is very simple. Okay, I will just maybe go through this with this way. I think it can come here now. See, N is obviously L cos alpha, because if you look at this, N is L cos alpha, okay, plus D into sin alpha. See, this N is L cos alpha plus D sin alpha, because this is my angle alpha. Similarly, T is going to be T is this side, T is going to be D, this is alpha again, D cos alpha minus L sin alpha, and of course in terms of coefficient it becomes like that. Okay. One more thing is important there, probably I should say, no, see, supposing you call this distance to be A, this distance to be, this is my center, actually this point is my center of pressure, where all these forces are, having done everything, is the center of pressure from where the entire force vector is acting. Let us say that this is equal to E. So what is my, another one important point is, what is the moment coming on this stock? Remember, this is my stock here, on which this force comes here, and I want to find out moment coming on that stock. That will be N into this distance. The moment coming will be N into E minus A. So the moment here I can write moment of that equal to N into in fact moment on the stock, that let me call this rudder stock, into E minus A. This is important sometime, because you see this moment that comes is the moment. See, there you have got a rudder and they have got a steering gear machine that you have to turn. So it has to turn against that kind of moment. So you see, you are turning this rudder about this point like this, okay, and the moment that you need, as if you have turned so much, the moment that is coming on that is so much, therefore you need that moment, because that much of moment to apply. So this is necessary for your steering gear design, that is why you need that. Why I am saying that is because in the rudder design we will find out that essentially if you can estimate this L etc. from every section, you can integrate and you can get the rudder the entire rudder's performance. The hydrodynamic performance of rudder can be obtained by actually taking section by section the CL, CD values, and then of course adding up all. Okay. So now, having known for a given section this rudder, what we need to know is to kind of define some of the quantities of rudder, some of the typical geometric definition. So that I will just try to draw a little bit here. See, if this is a most general case we are trying to write here. So here is a section. The top one looks like that here. This is my that stock point here, okay, what which is rotating here. First of all, this is my axis of rotation, okay. That is the spindle. This is my center plane. This can be called, this is root section, okay. This is the tip. See, there is some definition, okay. Any aerofoil section from which the direction in which its flow comes you call leading edge. This trailing, you must have been hearing whether leading edge, trailing edge, root section, etc., etc. So maybe let me not go to that. This is tip, this is root, etc. So for rudder, typically this length is what is known as chord length. Okay, so this is root chord. And this is tip chord. This distance is called chord. This distance is called thickness. Where the maximum thickness occurs, you call maximum thickness. Okay. Now, okay, actually, in fact, we should draw a line here also in the mean line. If you see here, it will look something like the rudder will be looking something like that. It is, you know, the thickness also comes down as you go down. There is a thickness here. This is my mean root thickness. This will be of course my tip thickness. And typically what happened, you see there is a line defined for the geometry, that's what will be new for that. If you take a line 1/4 of this, that is this is the distance here, let me call this CR. See, this root chord is say C root and this is say C tip. So if you take a point here which is CR by 4 and if you take a point here which is CT by 4 and if you join this line, okay, this is known as a reference line, and this angle, this is
Taking from the leading edge, CR by 4 and CT by 4.
yeah
From the leading edge.
yeah. This is known as a sweep angle. And then of course you will have some kind of center of pressure here. Let me put this as span. I'll let me write it all down and then I will just tell you. Then this is chord. So somewhere here maybe, no, not this point. Let me see. Then you of course have this CPC and CPL. This is it is getting all complicated, but anyhow. See, I'll tell you without making it any more complicated. See, it is something like that. Right now, here I am trying to introduce some geometric terms to define the rudder geometry. Why? We will find out that for each section, we have seen earlier that the forces that come on that section can be expressed in terms of CL and CD for that particular section. Okay. Let us say you have found the CL and CD, then you can resolve them into any direction that you want. Now you are doing this for a section. So if you want to do it for the entire radar, then you have to do for each section and add them up. Okay, you can integrate them along the section, and therefore you need to have some kind of idea regarding the geometry of the radar. What are the parameters that are basically used and based on which you normally have this radar force estimation, etc. That is what I am trying to say. Now in any aerofoil or hydrofoil section, this length is known as the chord length, this is the thickness. Okay. So therefore here this is my chord length, any measurement along this width is a chord length. So this top one is known as a root, this is a tip, so there is obviously tip chord length, this is a root chord length. Okay. And if you take the average of that, you have got a mean chord length somewhere, because I am just showing in this two way. Now this radar is shown to be having a some kind of a angle. See, it is not a straight line, it's having some angle. Okay. Now I need to have some kind of a numerical measure to know how much it is angle. You know, see, it is not straight line, this is having an angle, this is having an angle, and this diagram. Okay. So we need to have some parameter trying to say how much it is inclined. So that is done by taking 1/4 of this from this edge, 1/4 of this from this edge, and drawing this line and finding out how much this line is inclined with respect to the vertical. This is known as a sweep angle, which tells me approximately what is the orientation, what is the taper. That is all. See, it is just you have to think it this way. These things are, you know, if you think intellectually or from your mind, it is simply one measure of trying to find out how much it is tapered.
So the central axis in the dotted line of
This one is the line where about which it is.
the point of intersection, does it have any relevance?
This intersection, no, there is no relevance at all. It may not be here, it may be actually on this line only. It is just to show for my easiness that it is here. See, it need not be at, you know, it can be, suppose if there is a radar here, something like this and this. So this sweep angle is going to look something like that, and this stalk may be here. It is just to show how much is angle. See, there are two lines there, so the standard has become that you take 1/4 of that from each and take that line and find out how much that line is inclined with respect to vertical. That is all. Then you have got here a, you know, point where the entire force will act. You can call it center of pressure or center of force, and now you measure the center of pressure's chord length, and you know, like you have to now you see define where it is located. How do you know? For any point, location is x and y coordinate. So here the coordinates are measured of, you know, how much it is from its mean, that line here, how much it is from one edge, and how much it is down from the top. So you can call this length to be CPC, chord length, you can call it CPS, that is the length along span. This side is as chord, this is known as span. Okay. And there is obviously aspect ratio, there is a thing for this thing is called S mean by chord mean. See, once again the dimension of the radar in this, how high the radar is, the measurement of heights is called span, measurement of width you can call to be chord. Obviously it is varying, therefore you have a mean chord and a mean span, and the chord by span by chord is aspect ratio, as you know, for a rectangle. So you can, you see, you get an idea. What? Aspect ratio, it is a typical word for aspect ratio. Any measurement along the, if I call this to be C, if I call this to be say Z direction and this to be say X direction, any measurement along X direction is called the chord. So center of pressure points have got X coordinate. So I, you know, from with respect to this mean H at the end, we call that CPC, this is called CPS, etc. In essentially we do not have to worry about all this stuff, it is simply to tell you that you know, the typical feature associated with this has to be some kind of measure of geometry, means some kind of width and some kind of height. So the width and height are all this span and chord.
Aspect ratio we are taking Z by X.
Yeah, this by that, this by that, Z by X aspect ratio. If you, this is again in, you know, like a question of standard. If you take this by that, then also aspect ratio one can say it is a rectangle. You know, you can kill long side by short side, or short, you know, now on the other hand you can make this side short, that side long. So it does not matter, and the area of that radar, which is very important, AT, radar area, is of course the mean chord length into mean this length. You know, because it is rectangle, that area, this area becomes very important. why we are introducing all that is because we will find out that later on there can be many empirical formulas available where you can find out the total force based on these parameters. See, we have seen earlier that actually for individual section CLCD can be found out. So, what one can do, of course, go to a longhand and try to find out for each one CLCD and then resolve the forces and integrate them, long way the procedure. Okay. On the other hand, there are some empirical formulas that has been found out when you have this parameters known, length, breadth, mean chord, mean point, etc. You can estimate what is the total force coming or total CL for this, overall CL, not for individual section. The CL meaning the net force coming on that if you have turned the rudder, because after all the turning the angle of attack is going to be same, because this section or that section or this section, any angle of section you take, angle of attack is same. So, those directions are same, these directions are going to be same. So, instead of getting this CLCD for individual section, you can actually find out the total CL and total CD in terms of the entire propeller by means of empirical formulas, which is nothing but integration of. That is why I introduced this sort of things here. In fact, if you look back at that, we will find out that where is this formula again? L cos n. This n is the force coming along this direction. Okay, it's a normal force coming, normal to this, which is equal to L cos alpha plus D sin alpha. As we have shown here. Yeah, let me do it again. It's all getting confusing. What I wanted to say is that see separately again what we have done. We express the rudder forces in terms of y delta r into delta r. Okay, that's what we said. Here the rudder angle, if you think that the ship, the ship is here going straight line and you have turned it, therefore alpha becomes the rudder angle. Okay, approximately. In fact, in reality it may be more complicated than this, but maybe approximately alpha is the rudder angle. All right. Then obviously the I want to find out what is y the rudder force in the y direction. Okay. Then it turns out that you can find out them by resolving this L and D type of thing. The flow comes this side, the ship is along this side, we can find it out. So, you can actually find out, resolve them in terms of L and D. I need to see this picture here, just one second. Okay, I will show this little more in detail. Just think, as far as we are concerned for the class, all we need to know, all we need to find out is that for each section, I know for specifically that there is a force which is normal to the direction of velocity, which is called L, and along the direction of velocity, which is called D. And once I know two components, I have known the total force. After all, remember that the fluid gives a net force vector, and then I can resolve that in any direction that I want. And some of the direction of the force will become y, some of them will become x, drag force. This is the essential point that I wanted to make here. There are more complicated diagrams that one can actually tell. For example, a ship can be moving in this direction in a tangential fashion here, or rather ship is moving in this direction with an heading angle here. See, the ship might be moving in this direction, velocity vector. Okay. When he is turning, the ship is moving this direction, this is my trajectory, the ship is turning like that, but and the velocity is this direction. The rudder is of course here alongside this direction. Okay. So, my rudder is like this angle is my rudder angle, alright, but the flow comes to it along this direction, parallel to that along this direction the flow comes, V comes here. So, this is my angle of attack. Therefore, I can find out now from there the forces etc. This is V coming here. So, therefore, the force in the normal direction to that, normal to V, let me see, draw it here, this and this becomes lift and drag. etc., etc. I am not getting into the detail. All that I want to tell you, this becomes a little more complex for you to see. See, I will just explain to you just this diagram in a very, very brief thing. See, maybe I should draw it again. Just think of that. This is my ship. All right. Which direction the ship is moving? When it is turning, we have shown that the ship is turning with, what is the blue one? A velocity this side. That is why the trajectory looks something like that. It is turning. Okay. This is my longitudinal axis of the ship. So, as far as the ship is concerned, we are calling this to be actually the drift angle beta. All right. Just see one by one this point. Okay. Now, this was turning because the rudder was in this direction. Okay. So, the rudder, what is rudder angle? Rudder angle is obviously the angle it makes with respect to the ship, that is, this angle is my rudder angle. All right. Now, think of that, rudder is like that and the velocity is like that. So, that means the force that, see, the ship is moving this side means the flow is coming along this direction. That means on this you can say the flow is acting to this, the green one I can put here, along this direction to the rudder. So, what is the angle of attack? It is this angle. Is the angle of attack alpha for the rudder? Okay. What is alpha therefore? Now, you can make out alpha in terms of delta and beta, because you see you can easily make out, because this V goes here, this angle goes here. So, along this angle you can make out, you can express alpha in terms of so the angle of attack, as we have found out here, this alpha is not the rudder angle exactly. This can be, this we can find out this to be, I am not doing it here, but I think I can find out this to be simply beta plus this, let me see this, with the diagram here. This is delta r here, this is this angle. So, delta r is actually this angle. So, here the alpha V is this way. So, this angle is the beta angle. So, in fact, you will find alpha becomes sorry, the delta, what is alpha? V is this one. So, V can be plus this one. We can make it out, beta r plus epsilon. Let me try to find out beta r a rudder geometry and all that. Let me not get into this right now, but what I am trying to say is that you could easily find out the alpha is in fact this velocity is this side, that is this one velocity, alpha is this one, this is my angle of attack alpha, and this probably is the other angle. You can express that in terms of delta and beta. Okay. So, therefore, what happens is that you know now for a section what is my effective angle of attack with in terms of the rudder angle beta r and the drift angle, rudder angle delta r and drift angle beta. So, you will know the angle of attack. Once you know the angle of attack, obviously you can find out CL and CD. Once you know CL and CD, you can find out what is my total the forces coming on that, and once you know the forces coming on that, you can find out what is my net y force, because ultimately I want to find out what, see this is my x axis here, I want to find out what is my force coming along y direction, that is what is my y rudder. Okay. This you can find out in terms of CLCD etc., and this y rudder is y delta r into delta r, therefore, from there you can find out y delta r. So, the essential point is that you can ultimately find out what is the rudder force that is coming in the direction y and in the direction x by simply taking a geometrical consideration and trying to find out geometrically what is my actual angle of attack, and then resolving the forces along the desired direction. There are some simple very simple algebraic expressions for that. So, what you need to know as far as the class is concerned, the principle is that for any section, if there is an angle of attack known, you can find the force coming on that in terms of CLCD. Once you know the CF forces coming on certain directions, you can resolve them in any direction that you want. So, for a rudder behind a ship, you can find out what is the angle of attack in terms of the rudder angle and the drift angle of the vessel. So, once you know the angle of attack, you can find out the CL and CD and the lift and drag forces in terms of CL and CD. CL and CD will be known from tables of standard sections for which you have used the rudder. See, you would have used the rudder design based on some section, you know. So, you know CLCD. So, from CLCD, let me write the steps here actually. So, you will know or we know drift angle beta, rudder angle alpha. From these two, we will know angle of attack alpha. We know beta, we know delta, so we will know angle of attack. Once we know angle of attack, we will find out for that angle of attack what is my lift force, what is my drag force, because we know CL and CD. Once you know these two, we can find out what is my N force, what is my T force, etc. And from there we can find out what is my Y force, what is my X force, simply by resolving. Once you know what is my Y force, what is my X force, the Y force is my Y delta R delta R. So, I can find out Y delta R. In fact, I can find out what force comes on rudder, how much of that force is causing it to turn. And if you look at this diagram, you will see obviously the Y force ultimately comes this side, and if this is a ship CG, this Y force into this distance will be the one turning moment. See, ultimately you have got a ship here, there is a force coming this side Y force, there is a force coming this side rudder X force, and this force is going to cause a moment of N. So, you can find it all out. Okay. So, it all comes down to simply trying to take some kind of resolution of this rudder to various angles, etc. Therefore, I just want to tell you very quickly what can be the rudder force sort of formulas, okay, in terms of CLCD, which will follow from this definition. If you have this definition, you can have some kind of formula. We will not write the full formula, but all I wanted to mention to you is that empirical formula have been derived where you can find out the force coming on that in terms of the combined CL of this, which is written for example as CL is of course lift by half rho into area T into V square. People write that a formula looking like something like this. One of the formulas is C cos omega this thing A E square by etc., etc. All I mean, let me not go into all so much detail. See, the question that remains is something like this. You see, you will be knowing you are interested for the rudder at the beginning to find out what is my okay. let me see from the end. I have a rudder here. I want to find out if I give the rudder angle of delta r, what y force will I get? Because you see the formula of turning in my all the turning, it is yr delta r was the rudder force. So to know y force, I have to find out what is my lift and drag on the rudder. Conversely, if I know lift and drag, I can work out y force. To know lift and drag, I must find out what is the velocity magnitude and from which angle the flow is coming, that is angle of attack alpha. Okay. Now, supposing I I said that before, you can find out angle of attack in terms of heading angle, drift angle, and in terms of your rudder angle. So, these two will give you angle of attack, fine. You know the velocity of turn, fine. So, I can find out lift and drag. Now, I could find out for a section. Now, I have this kind of complicated section. So, somebody has given a suggested formula is that you can use this formula. Why this formula? Because this formula takes care of the fact of aspect ratio. There somewhere there is an aspect ratio there. It takes care of the fact of sweep angle. So, in other words, it is an empirical formula for getting lift, okay, in terms of those parameters. Normally, you would have used a particular I should say section shape, maybe NACA 1055 or whatever, some section for which you would have had a graph where the CLCD for that particular section is known. Now, if you now have a geometry with all kind of combination, you can actually use those formulas, something like that, where somebody worked out it looks a good fit, which you can find out for the entire section what would be my total CL, effective CL, which means I can get the L, lift force. Not only I can get the lift force, there are actually similar empirical formulas by which you can find out where is my location of center of pressure. Okay, there are same formulas given where is the location of center of pressure. So, once I know this location of center of pressure, I can find out what is the net moment coming on the rudder stock, which is I mentioned there that it is something like n into this distance. Okay. This is what we can do initially, because by doing this you have a quick estimate about the rudders working. I am not sure if I am kind of making it clear, because as I said, there are too many things to be squeezed in too short a time, so that it becomes a little problem. But the essential features therefore that I wanted to mention goes like this, that you need to find out the force coming on the rudder, because more the force better it is. You can use this, and the force comes for lift and drag. There is a drag also coming. See, when you turn the rudder here, there is a behind the ship here, then it increases my resistance. That is the reason why actually my ship slows down. You want it to slow down less, but you want to turn more. So you have this CLCD phenomenon. This is why you have not put we have gone from a plate to a aerofoil section. There was a long time you see in boats you have got simply a plate, because a plate also is an aerofoil section with an angle of attack. If you simply take a flat plate also like that, it will also produce a lift and drag.
Lift will be less.
Much less, and so it is less effective. That is why we use aerofoil section. But you know, this ordinary plate is very common. You can find it your country ports. Just put a plate there. So once you have this lift and drag for each sections, then you can add them up. But a better thing that has been done here is that for a typical rudder section, the integrated lift and drag could be expressed by means of some empirical formula, which takes into account the geometric features such as aspect ratio, such as your various other that sweep angle, etc., etc. This is only a question of applying a simple formula to a rudder. I mean, for designing purpose. This is the reason why I don't want to go term by term, because going term by term, the class gets an impression that there is nothing better. But the point here to tell you that as on now we have an empirical formula somebody suggested. Tomorrow you may suggest a different formula. It is simply that the empirical formula empirically corrects the lift and drag, or gives you a lift and drag based on various geometric features. In fact, earlier days, even before that, there was a much simpler formula given where the rudder force could be simply said to be something like some constant into AR into V square into delta R. In fact, long back people were using some standard formula. Again the rudder force will be equal to, see, rudder force, okay, the net force that comes on the rudder with knowing the direction, the rudder force will come up on the, basically it is the normal force here, okay, or X force, one of this, does not matter depending on the constant. It was estimated to be as some kind of constant, that is the coefficient into area of the rudder into V square into an angle delta R, okay. Like that it was doing. In fact, if you see that, this will turn out to be same thing as CD, and this constant was suggested to be something like 21.1. People have given various suggestions, 19.1. From that onwards, people have actually improved, and this formula is an improved formula. To sum it up, last sentence, to sum it all up, rudder produces force because of its aerofoil action. So, the force is lift and drag. Traditionally, lift and drag for aerofoil sections are always expressed in terms of CL and CD, which you know for known sections. We do not have to calculate ourselves, although it can be done today using sophisticated fluid mechanics calculation procedures, but you do not do it. So, once you now know CL and CD, you can find the lift and drag on a rudder section. Once you know that, you can find out what are the forces coming in any direction that you want. To know that, you have to know angle of attack. To know angle of attack, you have to know rudder angle and the drift angle, and there can be some other angle also, it is geometric correction. With all that, you can easily find out rudder forces coming. To make it even better, if there is a rudder where the cross sections, whether the length and the dimensions change, there are geometric features, top is wider, bottom is narrower, etc. You can find the combined CL and CD in terms of some empirical formula which corrects on those sectional CLs by using geometric features, aspect ratio, sweep angle, etc., etc. So, once you get that, you have this diagram, you get CLCD, you get LD, you find NT, you find Y, that is it, and that is how you are basically, you can estimate this rudder. If you want to, do not want to even spend that much of effort, you can go even lower down and have a even simpler estimation, but as you know, simpler the estimation, it is more approximate. So, as you go up more, you have more sophistication, and today in fact you can analyze the rudder by using far more sophisticated fluid dynamics theory, and that is where I will end, because 1 hour class you cannot do any more than that on rudder. Thank you very much.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the NR Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today IIT Kharagpur has blossomed into a time-tested, venerable institute of learning, with the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber-optic linked residential quarters for the faculty
आदर्शाय मादर्शाय प्राणदास्मह्वयम् योगकर्मसु कौशलम् योगकर्मसु कौशलम् योगकर्मसु कौशलम्.
Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.